Hello there, YouTube. My name's Don Brody, and I'm here presenting on behalf of my fellow teammates, Chad Bonadonna and Alejandro Lopez, and our sponsor for this project, Chapter 571 of the Experimental Aircraft Association. Today I'm here presenting our project, the design of a low-cost general aviation flight data recording and analysis system. So the first question that comes to mind when I think of an experimental aircraft is, what is it? An experimental aircraft is a primary category governed by the FAA. What these aircraft are generally aircraft that are built by amateur builders in their garages, just guys sharing a love for aviation. Two subcategories of this primary aircraft category are the experimental amateur built and the experimental light sport aircraft. Combined, these two subcategories of the experimental aircraft make up 87% of the experimental aircraft market. And in order for these aircraft to be classified as one of these two subcategories, they have to be 51% built by the amateur builder, and they can be built from prefabricated kit, original design, or purchased plans. One of the big problem that we're seeing with these aircraft is that they have an enormously high accident rate in their first 40 hours of flight. These first 40 hours of flight are when these pilots are parameterizing their aircraft in accordance with the regulations by the FAA, and this is what is considered phase 1 flight testing for these pilots. Their accident rate during this first 40 hours of flight is 350% that of the general aviation fleet. But the question then is, why is this accident rate so high in their first 40 hours of flight? Well, the problem comes from the current phase 1 testing process. Currently, when these pilots decide to parameterize their aircraft, they have to first manually construct a set of flight plans before flying their aircraft. And when they fly their aircraft with these manually configured flight plans, and while they're in flight, they have to manually jot down notes of measurements from their instrument panel on a pad of paper, normally strapped to their thigh with a pen. When they come down from the flight, they have to manually calculate all the measurements and parameters for their aircraft, generate their own manual graphs, manually compile their own pilot's operating handbook, and then submit all of this stuff to the FAA for approval. As we can see, one of the main problems here is that there's so many manual steps in this process, and all of these manual steps lead to compounding error in parameterization. So what does this compounding error in parameterization lead to? Leads to loss of control in flight. Loss of control in flight is defined by the NTSB as an accident that it takes place due to insufficient takeoff speed, early rotation, too steep of a climb on takeoff, inadequate airspeed, all of these leading to aerodynamic stalls. For the experimental amateur built aircraft, between 2001 and 2010, 44% of all fatal accidents in the experimental amateur built aircraft market were due to loss of control in flight. So this leads us into our problem. We see that this lack of aircraft parameterization leads to loss of control in flight accidents, which leads to this much higher accident rate as described previously. The NTSB has done a study on this exact topic and found that the use of recording devices can significantly enhance the monitoring of parameters. But unfortunately, there's two problems with the NTSB's recommendation, and both of them have to do with the device they recommend to fix this problem. The first problem is that the device that they recommend costs $2,600 plus installation. This cost can be up to about 20% of the average cost of an experimental aircraft. The other problem is that the device that they're recommending for these pilots to use is not purpose-built for their system. It must be retrofitted to fit their needs. And so what we're realizing here is that this high fatality rate coupled with the high cost of recording devices and the lack of a purpose-built system leads to the need for a system that is purpose-built for these pilots. And that leads us into our proposed phase 1 testing procedure. We're proposing that these pilots use an entirely different method of parameterizing their aircraft based on a system of automation. The first step of this automated process is to generate flight plans in an automated fashion. The pilots input their parameters, such as the altitudes they're allowed to fly at, how far away from their airport they can fly at, and the automated flight plan generator generates a set of flight plans to stick with these pilots throughout their flight, the course of flight for their first 40 hours. Additionally, there's a device that would go into their aircraft that would automate the process of monitoring aircraft measurements, acceleration and velocity, for instance. When the pilot comes down from these flights, they hook the device into up to a computer running the software that would be part of this system, and the software analyzes the raw data from the device and begins to determine the aircraft characteristics over the course of them flying all of their flight plans. A pilot's training record is generated, as well as a pilot's operating handbook. The pilot's training record, although it's in itself a training record that keeps track of what happens during flight, is not unique. What would be unique about this, what would be new about this, is that the software would also determine if the pilot has made any unsafe acts during their flight. So for instance, if a pilot were to take off at 1.1 times their stall velocity, the software should recognize this as an unsafe act and a potential for loss of control in flight, and alert the pilot to this before their next flight so that they can correct it and take off at a safer takeoff speed, for instance, somewhere around 1.3 times their stall velocity. In addition to adding safety and automating this process for these pilots, it also streamlines the process of submitting this Phase 1 testing paperwork to the FAA for approval. Today, however, we'll be focusing in on a couple subsets of this system. One of which is the device subsystem, where we'll be trying to determine our requirements for such a device, and the other is our pilot's operating handbook, which we'll begin with. So during the course of this project, we generated our own Excel spreadsheet written in Visual Basic that helps us determine aircraft flight characteristics based on different inputs that the pilots could make after flight. And we did this to determine what measurements would be necessary to generate all the characteristics needed during the running of this system. The first one we have here is our rate of climb graph. For the rate of climb graph, we realized that we needed to have 3-axis velocity, 3-axis position, and that we would hope to mitigate the risk of too steep of a climb on takeoff, the loss of control risk of too steep of a climb on takeoff. The next one we have here is our stall speed. The stall speed is one of the most important graphs in a pilot's operating handbook. If the aircraft is stalling, it's inherently a loss of control in flight type accident. So we hope to mitigate the risk of inadequate airspeed, and we realized that the measurements that we would need for this to determine all these characteristics would be 3-axis velocity, 3-axis position, the bank angle of the aircraft, and we also would like to know the force being applied to the pilot. And this leads us into our device then. So when we began determining what we would need to put inside of our device, this helped us obtain our suitability requirements from you see here in the value hierarchy. When we looked at the measurements that would be required for the pilot's operating handbook, we could see that we need inertial readings from an accelerometer. We need rotational readings from a gyroscope. We need altitude readings to help with our precision, at least from a barometer. And we need a GPS in order to determine our lateral coordinates. We as subsets of this, we need to know both their sensitivity and their range of operation. Next, we have our usability requirements. Our usability requirements have to do with any way that the pilot would have to interact with the device and or software. We found that this is, from our decision maker, we elicited these weights using swing weights with our decision maker, and we found that usability was very important to these pilots. The main reason is because they have many different kinds of aircraft in this category that are shaped in all sorts of different ways, but they're all pretty small and compact. And so we wanted to make sure that that this device would be able to be mounted anywhere in the aircraft. It wouldn't have to be mounted in a certain position, and this would allow for a pilot easier access of this device for a pilot. And also, we wanted to limit the interaction by incorporating as little interaction from the pilot to the device as possible in order to record the readings. And under portability, we considered battery life, data storage, and weight, all of which are very important to make sure the device can be moved from aircraft to aircraft. When we took a look at what was out there as a possible subset of representative subset of the different types of device platforms that we could use, we determined that a microcontroller, a smartphone app, and a microprocessor would be a good subset. For the microcontroller, we chose the Arduino, which is a very popular open source platform, which we'd be able to configure with all of the hardware we would need for this as a prototype for $105. The iPhone 6 app was chosen, or iPhone 6 smartphone, writing an app for that was chosen as a platform due to the fact that most smartphones don't have a barometer, but the iPhone 6 does. And not only does it have the barometer, but it has a very large market share out of the phones that do have a barometer. Most phones have accelerometers, gyroscopes, GPS, most smartphones at least, but not all of them have the barometer we needed. The cost of this iPhone for prototyping would be $650. And then lastly, we chose the Raspberry Pi for our microprocessor, also a very popular platform similar to the Arduino in cost and functionality, but except for the fact that it has onboard data processing. We'd be able to configure this Raspberry Pi microprocessor platform with all the sensors that we need for a total prototyping hardware cost of $175. When we stacked all these together and we took a glimpse at their utility, at their cost, we found that the Arduino with the GPS was the second lowest cost and the highest utility. And for that reason, we decided to go ahead and prototype during the winter break with our Arduino Uno. We found, however, over winter break that the Arduino Uno didn't have the real-time processing capability that we needed in order to generate the measurements and parameters that we needed to generate. And we found out the reason for this is because it doesn't have enough static memory. It doesn't have enough random access memory. And so we learned from that prototype and realized that if we wanted to prototype again, that the Arduino Mega would be a much better platform because the Arduino Mega has 4 times the random access memory as the Arduino Uno, costs only a few dollars more, and it should based on the amount of memory that we need to use, the Arduino Mega should work. However, we did not want to risk the chance that we would fail a second prototype and get set way back behind schedule. So instead of prototyping again with the Arduino Mega, we went on to build our own simulation. Our simulation is set up and it's written in Java, and it interfaces with MATLAB basically just to give us some pretty graphs after it's done doing all the computation. But this Java simulation takes in a set of inputs. The inputs to include device parameters, random number generator seeds, and configuration variables. The device parameters just have to do with our GPS accuracy, accelerometer sensitivity, all the different sensor sensitivity inputs. The random number generator seeds are there so that we can make our simulation replicable. And the configuration settings are there to allow us to adjust certain input parameters that affect the simulation, such as the sample rate, which is one of the most important ones here. And the reason it is because our sample rate here is set to 5 readings per second. In our simulation, it could be set to whatever, but in the one that we ran, it's set to 5 readings per second. And the reason being is because in real GPS sensors have a reading limit of 5 readings per second, and we wanted to make this as true to life as possible. The last configuration setting we have is our flight plan, and that flight plan it gets sent into our raw data computation of our portion of our simulation. Inside of there, stochastic error is added to the flight plan based on the device input parameters. That stochastic error is saved into a raw, or with the flight plan, the entire raw data is saved into an XML file and sent over to the second portion of our simulation, which analyzes the raw data and attempts to reduce the noise. The reason that we're attempting to reduce the noise in the software is because we realized that if we want to keep with the low-cost constraint of our sponsor, that it might be best to eliminate some of that noise on the back end with our software at a low cost as opposed to investing in more expensive sensors that have better sensitivity specifications. So in order to reduce the noise of our simulation, we implemented the line smoothing algorithm that you see up in the upper right hand corner of the slide. What we did is a very simple line smoothing averaging algorithm where we took 5 readings, like the 5 readings per second from a GPS, and condensed those down into 1 reading. The benefits, there's 2 benefits to this. One, it reduces the size of the data 5 times, reduces the size of the data capacity that we need, but it also does a very good job of reducing some of the error and definitely the standard deviation of the different graphs by smoothing them out. The most dramatic of these effects is seen in velocity, which is shown here on the slide. And if you look in the lower left-hand corner, that graph is an absolute mess with a mean error of 12 meters per second and a gigantic standard deviation. Using the line smoothing algorithm, we're able to get this down to about 1 meter per second and have a much lower standard deviation. We also found very similar results with when we looked at our accelerometer and our gyroscopic sensitivity. Here you can see the output error percentage on the or output error on the left-hand side, and the accelerometer and gyroscopic sensitivity on the x-axis. On the bottom line of each one is our smooth data, and the top line is our raw data. So there's obviously been quite a bit of improvement, very similar improvement on both graphs. And one of the cool things about this is our trend here is linear. We have a linear relationship between sensitivity and error, which allows us to fit a linear trend line and determine exactly what our sensitivity requirement is based on a predetermined threshold. We predetermined our threshold to be 2.5%. When we plug that in to both of these equations on the bottom, we end up getting our actual requirements, which you see here. So this leads us to have to determine that our accelerometer requirement should be 0.16% sensitivity and gyroscope to be 0.08%. And these are both great results. The reason being is because in low-cost sensors on the market today, we find a lot of the accelerometers, most of the accelerometers come in at 0.1% or below, and most gyroscopes at 0.04% or below in sensitivity. So these fall well within those requirements. A couple other cool ones here are our battery life and our data storage, which weren't determined directly from simulation, but as a result of everything that went into the thought process behind it. And we found that for both of these, we wanted to limit the expected flight of these aircraft to 2 hours, and we expect all our flights to be within 2 hours, hopefully less, closer to 60 to 90 minutes. And we found that the current draw for the Arduino Mega for a 2-hour flight would be 140 milliamp hours, which is great because even a 9-volt battery falls well within that capacity. And for data storage, we found that we only need 76 megabytes to store all the raw data for a 2-hour flight, which is again great because that falls well within the range of even a small SD card. So now that we determined these requirements for our device, we could kind of move on at this point and see what it would cost to bring this product, this system, to retail. We found, kind of surprisingly, that the device cost, the marketing, flight testing, we put all this into one category. So all the prototyping and production cost only came out to about $400,000, which is great. That helps us keep within our low cost constraint. But the problem here is that we see that in order to develop a piece of software that would automate all of these different processes safely for these pilots, it would take an enormous amount of code, a lot of debugging, a lot of testing, and would come to a price of about $1.2 million. For total combined cost, estimated cost for this to produce this system and bring it to retail of $1.6 million. One other note about this quickly is that this was determined based on bringing the first 2,500 units to retail, 2,500 being about 10% of the experimental aircraft market. So what about investors? If we brought investors in to invest in this system, invest in this product, try and bring it to retail, when would they get a return on investment? We found somewhat unfortunate results here. Here we hoped that we could price this product at $500 and keep within the low-cost constraint of our sponsor. We find that even if we sell the full 2,500 units right off the bat, we don't even break even. So the more likely retail price point for this system is somewhere around $2,000, where an investor breaks even at 800 units and makes a pretty decent profit if they end up selling all 2,500, or if we sell all 2,500. So who are these other retailers? Who are the other retailers in the market today? We see here a bunch of currently available monitoring systems and a representative subset of those. The first one here is the Dynon AHRS unit, which was the NTSB recommended unit earlier in the presentation. And this is a microprocessor-driven AHRS device that is mounted in the panel of the aircraft and does in-flight analysis of the aircraft measurements. The next one is the SPGO LIPS, which is a microcontroller-driven device, also capable of doing in-flight analysis. The next is the Stratus 2, which is a very popular device among these experimental aircraft pilots. due to its low cost, and also its ease of use with it, the fact that it interfaces through Wi-Fi with an iPhone or an iPad. And the last one we have here is the Garmin Verb Elite, which is basically a video camera similar to a GoPro, and it can be mounted to view the aircraft instruments during flight, and after post-flight, those measurements can be compiled by the pilot manually to determine the aircraft parameters. Cool thing about the Garmin Verb Elite is that it also incorporates an accelerometer and a GPS sensor for time-stamped readings during playback. So we took all of these different currently available monitoring systems, and we decided to check their utility versus the Arduino-based system. We found that the Arduino-based system still is superior in its utility. However, at a price of $2,000, it does not meet the low-cost constraint that our sponsor set. For that reason, we have to recommend the Garmin Verb Elite to our sponsor. The Garmin Verb Elite is by far the lowest cost system here, or lowest cost device here, at $280, and can be found on sale for as low as $200. And in addition to that, it has the second highest utility outside or within the set of currently available monitoring systems. But we weren't really happy with this. It still gives our pilots a pretty low utility, even though it's low cost, and we wanted to try and do a little bit better. So we thought about this easyPOH system. The easyPOH system incorporates the spreadsheet that you saw the graphs out of earlier for the pilot's operating handbook, and those are generated by an Excel sheet written in Visual Basic. So the easyPOH incorporates this Excel sheet as well as a automated flight plan generator that users can use as well. And what we plan to do following this project over the course of this coming summer is finish building these products, testing them, creating our beta version, and putting them online so that pilots all over the world can use the system and use it for free. And if we give this system to pilots to use for free, we can increase the utility by 0.1 without increasing the cost of the Garmin. And this adds a ton of benefit to these pilots. It doesn't take out all the manual processes involved in determining aircraft characteristics, but what it does do is give them a good start, and it gives them a good start at a very low cost. We've actually already begun developing the site, as you can see here, and currently you can go to easyPOH.com. You can find this site. Maybe when you hear this video, we'll actually have links available for the links working so that you can go ahead and download the software. At this point in time, it's just a template, but by the end of the summer we hope to have a couple beta versions for both the flight plan generator and the POH generator up and working and available for download on the site. And our goal for this, our hope for this, is to increase sport aviation safety and give these pilots a way to improve their safety and increase their utility in this type of device for no extra cost. And with that, I will thank you very much for watching our YouTube presentation, and come check us out on easyPOH.com.